Okay, let's look at some Titanic data. And so here we're interested in whether the sex of a passenger is related to whether they survived. And so my 2x2 table, I've got female and male, and I have survived and died. And so what are the odds of surviving for females versus males? And so the odds ratio is going to be 308 divided by 154 divided by 142 divided by 709. And so 2 over 0.2 or 9.99. So let's interpret this. The odds of surviving for female patients was 9.99 times the odds of surviving for male passengers. So what if we wanted to fit a model? What would the equation be? And so in this case, it would be the log odds of survival. We'd fit that logistic regression model. And that's going to be beta 0 plus beta 1 times the sex of the individual. And so here's how we would do that in R again. And so I would start with that logistic underscore reg function. I'm going to set my engine to GLM. Again, that stands for generalized linear model. And I'm going to fit my Y variable is survived, my X variable is sex, and my data is going to be Titanic. I'm going to use the tidy function to tidy this up and get a nice output. And so looking at this output, what is my referent category? My referent category is male because the results here are in terms of female. Okay, so how do we interpret this result? We get this beta coefficient of 2.30. What does that mean in the context of logistic regression? Well, we could exponentiate this. We could exponentiate that 2.30 because that's going to say the 2.30 we know that's the log odds. And so the log odds of surviving, given that you're female, is 2.30. But let's talk about it in terms of the odds. And so if you remember from that table of how we convert log odds into odds, we need to exponentiate it, which in R we can use the exp function. So we're going to plug in that 2.30 and we end up getting 9.99, the same thing as we got from our 2x2 table. Similarly, we can exponentiate everything in our table by using the exponentiate equals true argument in the tidy function. And so this is really handy so you can avoid having to do it by hand. So we end up with that 9.99 there. And so that tells us that the odds of surviving for female passengers was 9.99 times the odds of surviving for male passengers. What if the explanatory variable is continuous? So here's another data set here, here I'm going to do logistic regression again, and I'm still setting my engine to GLM. I'm fitting acceptance. So in this question, I'm looking at med school GPA, and I'm trying to see if GPA is associated with whether or not you're accepted into medical school. And so this is the GPA in college, and this is an acceptance 0-1 variable. And so I'm going to fit this model here where acceptance is my outcome and GPA, which is a continuous variable, is my X variable. And so I end up with 5.45 as my coefficient. And so a 1 unit increase in GPA yields a 5.45 increase in the log odds of acceptance. So that's how we would interpret this on the log odds scale. But now let's exponentiate it so we can interpret on the odds scale. Wow, that ends up being a big number. So this ends up being much bigger because of the units here. And so a 1 unit increase in GPA yields a 234-fold increase in the odds of acceptance. So you'll notice this number here is 234 because we've got this E plus 2. So we've got this is 234 is my exponentiated version. So that seems huge. Remember, the interpretation of coefficients depends on your units, and this is the same in ordinary linear regression. These estimates are all dependent on the units of the X variable. And so we could change this to instead we could get the odds associated with increasing GPA by 0.1. So that would be, we could exponentiate. So if we exponentiate this is a 1 unit increase in GPA. If we exponentiate this, 5.45. But if instead we want to know a 0.1 increase in GPA, I mean, a 1 unit increase in GPA is pretty huge, going from like a 3 to a 4 or a 2 to a 3. That's a pretty big increase, especially because GPA really ranges from 0 to 4. But a 0.1 increase, that's a little bit more meaningful, going from like a 3.2 to a 3.3. And so to do that, we're going to multiply inside this exponentiation, we're going to multiply our coefficient, our log odds coefficient, 5.45, by 0.1. And so that's going to get us a 0.1 increase in GPA. And that results in 1.73. And so if we were interpreting that, we would say that a 0.1 increase in GPA yields a 1.73-fold increase in the odds of acceptance. And so we could also do this by just changing the changing the data set so that we have basically GPA that's goes up in tenths of units. And so we would do that by just multiplying by 10. And that's going to get us the same answer. So basically, the only difference here is I'm mutating this data frame to include a new variable called GPA underscore 10. And this is just GPA multiplied by 10. And so now if I plug that value into my model, that's going to give us the same answer, because now a 1 unit increase is really a 0.1 unit increase on the original GPA scale. And so we still show that a 1/10 unit increase in GPA yields a 1.73-fold increase in the odds of acceptance. Okay, so what I want you to do is I want you to use the default data from the ISLR package, and I want you to fit a logistic regression model predicting whether a customer defaults with whether they are a student and their current balance. And then I want you to interpret these beta coefficients. I want you to interpret the confidence intervals. And then I want you to try to see if you can get odds and interpret those odds ratios as well. So here's some code to get you started. The dataset default is in that ISLR package, and then you can do data and then in quotations default to get to pull that data. And then go ahead and fit that model and interpret those results. So do that in the same application exercise that you had already started, and when you finish, knit it and turn it in on Canvas.